Hello, my dear, and let's start our lecture number 6 on hypersonic dynamics. 1 second, please. I just share it. Today we will be continuing study hypersonic inviscid flow field. And let's start with hypersonic small disturbance field. You know, if we return to our roadmap from our first lecture, we are presently working under the general heading of flow field consideration. And we have so far treated both the concept of Mach number independence and hypersonic similarity under this heading. Also, return to our chapter or module roadmap in this slide. Recall that we have discussed the general partial differential equation for an inviscid flow. It was on lecture number 4. Situated at the top center of this figure. From these governing equations, we have proven mathematically the existence of Mach number independence. If this you may see in the left box in this slide. We have also obtained the hypersonic small disturbance equation in the same lecture number 4, represented by the center box on this slide. It is important to know that in our discussion of both Mach number independence and hypersonic similarity, we have only examined the appropriate equation. We have not solved that. Hope you remember this. Specifically, our examination of a non-dimensional form of the Euler equations and the boundary conditions, the same on lecture 4, clearly demonstrated the mathematical justification for Mach number independence. Similarly, our examination of the hypersonic small disturbance equation and the boundary conditions in the same lecture has led to the important conclusion dealing with hypersonic similarity. But in both cases, we did not actually solve the governing equation. Okay? This is far as we can proceed in such a fashion. For the remainder of the items listed under flow field consideration in this slide, we will deal with actual solutions of the governing equation for specific cases. And this will constitute the remainder of the present module on approximate method, as well as all of the next lecture on exact method. So consider again the hypersonic small disturbance equation given by these equations 1, 2, 3, 4, and 5, yes? And the purpose of the present our module is to discuss how these equations can be solved for the hypersonic flow over slender bodies. The material in this module is a representative sample of a bulk of solution generated, let's say, over the past 40 years. All originated with this equation on this slide. Such solutions come under the general description of hypersonic small disturbance theory. And this theory was first developed in some detail by researchers Milton Van Tine. And we will partially follow his approach in this model. Okay? To begin with, consider the hypersonic small disturbance equation written for two-dimensional flow. And recall that the x momentum equation is decoupled from the remaining equations in the system. For this case, we have next three equations you may see here on the left upper corner of this slide, which are three equations to be solved for the three unknowns as V average, P average, and rho average. However, this system can be reduced to just one equation in terms of one unknown by introducing a stream function psi. F form is this one, rho average, d psi over dy average, and d psi over dx average will be minus rho average times average V average stretch. However, yes, this system can be reduced for this equation. To be a valid stream function, psi must satisfy the continuity equation. And substitution this equation yields that the psi is defined by means of next two equations. That does indeed satisfy the continuity equation. And using the subscription notation for partial derivative, and we become determiningly this equation. Also, denote that for the rho and pi rho average and pi average, we may found be using by omega as a function of c psi omega. And this is true because for an isentropic flow we can see on these conditions here is constant along a streamline. And by definition of a stream function, here psi is also constant along a streamline. And hence we can get these two expressions on the right side of this one. After that, we may differentiate and found next two expressions. Because the d omega or dy, it will be function in between omega, gamma, and psi, we may write the next three equations at the end. Okay? So if we substitute all previous equations and last one into the y momentum equation, we can get this interesting expression on the top left corner of this slide. Or after small transformation, we can get this expression in the next row is this one. So this last equation is a single equation for a single unknown, namely psi, based on the hypersonic small disturbance assumption. But you should note that in the development of this equation, no additional assumptions were made other than that of two-dimensional flow. And hence, our equation is of the same order of accuracy as the original hypersonic small disturbance equation. So once this last equation holds for two-dimensional planar flow, and hence it can be applied to two-dimensional shapes such as airfoil. But on the other hand, for axisymmetric bodies, a cylindrical coordinate system where we have x, r, and psi is more convenient. Here, x and r are the coordinates parallel and perpendicular, respectively, to the body's center line. And psi, I want only to remember, is the familiar azimuthal angle. Okay? For an axisymmetric body, at zero angle of attack is the same. The flow field is independent of psi and depends on x and y, in our case, r only. Okay? So for this case, the governing hypersonic small perturbation equations become as these on the left part of the slide on the bottom. These are the same equation as the previous slide, except for the additional terms in the first equation. In the preceding, x average, it was x over L. R average, R over tau L. And V average stretch is the non-dimensional perturbation velocity in the R stretch direction. And all of the other quantities are the same as before. So for the axisymmetric flow described in these last two equations of the bottom, a stream function psi can be defined in this very simple form you will see in the right part of this slide. Right? It's very, very simple. A derivation similar to this equation in the previous slide leads to the following equation for our axisymmetric flow, as you can see on the right bottom plate of our slide. Namely, this equation is the axisymmetric analog of the previous slide I just showed you. Is analog for this one. As before, it is a single equation in terms of one unknown, namely psi, right? So our final equation here is easier to solve than the original coupled system of the three equations. Okay, original, I'll just show you for 1 second. These original three equations, it's not very simple. So we will illustrate a solution this our equation for the case of a flow over a slender right circular cone at zero angle of attack. And for this case, we take advantage of the nature of conical flow, namely that flow properties are constant along any ray emanating from the cone vertex. Now, consider we have the sketch shown in this slide. Along any ray making a slope at exactly r over x with respect to the center line, yeah, r over x with respect to the center line, the flow properties are constant. And for this ray, we define a conical variable theta average, such as this our expression. In addition, for conical flow, the stream function psi, dependence from two variables only, can be expressed as a function of x average and unconvex from the theta. Yes, because we remember that R stretch, it will be X stretch times theta stretch, theta average, okay? A proper form for psi applicable to conical flow. Yes, to conical flow for the psi. And intuitive justification for our last equation can be obtained from previous figure. Recall that for two-dimensional flow, the difference in psi between two streamlines is equal to the mass flow between these streamlines. For an axisymmetric flow, the difference in psi between two stream surfaces is will be designated 1 and 2 in our figure. I just show you the previous. Designated in this 1 and 2, okay? If this is equal to the mass flow between these surfaces, and this mass flow is proportional to the circular ring of area between stream surfaces 1 and 2. Are you agree with me? Which in turn is proportional to R in power 2, and thus is the same as R average in power 2. And hence, it makes sense to define the stream function as psi will be proportional for the R average square times function g from theta average. So in our relations, R average square is proportional to the area. And so I mentioned just function g from theta average. It makes sense defined as a stream function. Where is our R average square is proportional to the area, and second component g from theta is yields the flow properties necessary to complete the mass flow expression. Okay? However, because we know that the R average is proportional as this simple equation to the top, and then we can find the relation for psi and relation for the psi function in this case. So we wish to substitute this expression for psi, and to do so, we need expressions for the derivative of that function psi, constructed in the following. In the process, but you should keep in mind that psi is the proportional this simple expression, yes, and that we are essentially transforming from one set of independent variables, namely X average and R average, into another set, the same X average and theta average, where our X average and theta average we already defined. So, for example, from the chain rule, we may write the expression d psi into the X component and depending on the theta and X. Here the subscripts are added to remind you that remind what independent variable is being held constant for each of the partial differential. From the next equation, as here you may see on the bottom, you may find this simple expression. Here we can find that using here function stretch from theta average, it's only as a df of the d theta, the first derivation. After that, we may find as expression it's d theta over dr for average. It's only as an opposite function for from the x average. Yes. So because x average is being held constant in our expression, then we from the chain rule applied for psi, we can rewrite the chain rule. We can rewrite our expression in these next. For more simplifying expression, we can write in this form. Also, from the chain rule, we may write expression not only for RR, and expression from R and X average. And you can see it's generally analogical in this one. What's the difference only? What's the difference only? Yeah, R average instead of X average. Yeah, only. And that's final. Instead of X average, we have R average. So from our equation, we can get our expression from d theta over dx for average R. This is negative function. But notice that that dx over dr, it might be 1, and utilizing previous expression here, in noting this, we become to this expression second derivation only, okay? Or we may rewrite in another form that express more tactical explanation for this. And similar, from the chain rule, we may rewrite the psi for x average in derivatives equation. Or simplify, or transforming it, not simplify, transforming it in this form. Or more bit of simpler form here on the bottom. And similarly, from the chain rule, from this expression, psi from double x, and from previous equation, we can get this net expression and got as the final expression on the right bottom form. Maybe a bit tedious, sorry, but you know, dynamics, we should know all the physical process in this. So here in our subject, we study not only aerodynamics, we use it as a thermodynamic, chemical dynamics, all of these compressing in hypersonic dynamics. So why we should use maybe a bit complicated mathematical approach, okay? So after proper substitution in our equations, we may get this expression on the top. This expression on the top. Or in a bit shorter form, not simple, but only shorter form, you may see as this for psi from x. So these get us completed all our derivative transformation. And all our substituting and noting that omega stretch is analog for d omega over d theta must be equal to 0 because the entropy, and namely omega, is constant between the shock wave and the body. And in this case, we may write as this final expression on the left bottom corner of this slide. Dividing by this expression by x stretch squared and grouping coefficient on like powers of powers of theta average, this becomes to the expression on this right side. Not very simple, but this reality. Next step, dividing this expression by x average squared and grouping coefficients of like power I just recently mentioned, theta average squared, this becomes to this large expression. We get this after recalling that relations between r over x average get us theta average. It's a logical, okay? And noting that the terms within the square bracket cancel each other. And our preceding equations becomes in this form, as you can see, more compact. Or after final rearranging, we may get this final equation on the right side at the bottom. Okay? So this equation is a governing equation for hypersonic flow over a slender cone. It was obtained from the system of hypersonic small disturbance equation. And indeed, it replaces the system with a single ordinary differential equation in terms of one unknown. It's our, namely, which unknown? Unknown from theta function, f from theta average. And when a system of our partial differential equation is replaced by one or more ordinary differential equations in terms of one independent variable. Yes, I want to repeat it. Then the solution is said to be self-similar. And such is the case here. However, this should be no surprise. The Taylor-Markov equation for the exact solution of conical flow is also an ordinary differential equation. And hence, our equation in a frame can be viewed as the approximate counterpart of the Taylor-Markov equation, applicable to hypersonic flow over slender cone. Our next step is treating our previous equation, is treated this equation to recall that omega is the same as the P over rho in power minus gamma, and to recognize that omega is a constant for the isotropic conical flow and equal to its value behind the oblique shock wave. An expression for omega can be obtained directly from the hypersonic shock wave relation derived in our last lecture. So, examine that equation and ensure that rho average and P average, respectively. For flow over a cone, the shock wave is a straight oblique surface with a constant transformed flow that we have in this equation, and that get us expression for dy over dx. Average proportions 1 over tau dy over dx. But for hypersonic flow over a slender body, we may recall that dy over dx, it's like the tangent of beta, or maybe approximately tangent of theta over c, or simply approximated as a tau. Here theta sub c is a cone angle, okay? combining these two equations, and remembering that the theta c is the cone angle, we see that dy over dx may be approximately equal near the 1. Inserting this result into our equations in previous lecture and returning to the definition of omega, we can obtain this expression on the middle left part. And noting that m inverse times tau, it gets us k. The hypersonic similarity parameter, the preceding equation, can be written as this form on the bottom left part for omega. Okay? Clearly that the omega is function from the k. It is a constant for a given flow with a given value of k. And reflecting again to our equation on the top, the solution to the flow field in the form of the function from the theta average will depend on k as a parameter, because omega is a function of k. And this is yet another example of the close relationship between solution of the hypersonic small disturbance equation, namely hypersonic similarity, and the hypersonic similarity parameter k. Okay? So the solution, our equation, must satisfy boundary conditions at the body and behind the shock wave. Now, let us address these boundary conditions by first noting the values of theta average on the body and at the shock wave. At the body, the surface of the cone with a semi-angle theta sub c get us expression in this case for theta average, okay? But however, from the picture, it's precisely get us as a tau. And thus, from the preceding equation, in case as a body for theta average as the same as a theta sub c average must be equal to E1. As the shock wave, with the wave angle beta, we can write at these equations here, 1 over t times r sub s over s. From our figure, I just want to show this figure for 2 slides or 3 slides. What this corner figure, okay? We found the beta angle and find the theta stretch at this point. Okay, 1, 2, 3. And we can get this expression into this slide. So, from our picture recently shown, and noting that for hypersonic flow over a slender body, beta is very small. In this case, we will rewrite r sub s over x, it will be tangent beta. But if it's smaller body, in this case, we may rewrite it depends only from angle of beta. And thus, combining the last two equations, this and this, we can write this expression for theta average, 1 over tau times tangent beta, or simply its relation beta over tau. So for a slender cone, we noted that tau is rc sub c over x, or tangent theta c, or approximately simply the theta sub c. And hence, we can written for the shock as our final expression on the right bottom column. Theta average will be depending as a beta over tau, or beta over theta sub c, or as expression shock angle over cone angle. What does give us? Let's say that the boundary condition for our equation are the known values from function of 1 at the surface and function from beta to tau and the same beta stretch to tau at the shock wave. And these values are known as follows. And first of all, at the surface, we know by definition of the stream function that c psi equals 0. And from this, we can apply at the surface, and we can have this expression on the left top angle. Psi might be equal 0. And thus, the body boundary conditions will be in the next row at the body function from 1 must be equal 0. At the shock wave, we can obtain values of both f and f stretch, but using our expression in the previous part, psi over x. Substituting this equation into the previous one from the beginning of lecture, we can get expression for psi in this one. After the next substitution, we can obtain next expression on the middle. Solving this expression for f, we can get here this more compact expression, right? At the shock wave, this our compact equation becomes as this one on the bottom. It has a bit different, not radical, but a bit different from this previous one. Okay, but however, we should note it as r s sub s over x for average. It's the same as a theta over s in average, the same as a beta over tau. And that allows us to write less over shock conditions expression in these phrase. Function from beta over tau proportional as the average rho over 2, an expression in this bracket. Okay? To obtain f stretch of first derivation, we can get this simple expression. At the shock, this becomes in the next expression here. And thus, finally, we can get as a for shock wave expression on the right bottom part of this equation. In both these two equations, the values of rho and v average and v stretch are those values immediately behind the shock wave. And recalling from previous equation, in expression that dy over dx must be 1, yes, as expressions here, and noting that m infinite times tau get us k, then our expression may be rewrite in expression in this form. Very interesting, we have for average rho, depending only from expression gamma plus 1 in denominator and gamma minus 1 in denominator, in expression on the brackets here. Okay? And using next, we may rewrite for the v average stretch will be proportional 2 over gamma plus 1. And in a bracket, second component, 1 minus 1 over k squared. So, in summary, the boundary condition will be given our two equations. Add the shock wave, wherein the values of rho average and V stretch average are given by these two equations. Okay? And now, in a position to set up a straightforward numerical solution for the hypersonic flow over a slender cone. In most practical cases, we are interested in the flow over a cone of specified angle theta sub c, or equivalently specified slenderness ratio tau, okay? And with a specified m infinity. Generally, all our expressions say, if we have Mach number more than 8, all parameters practically constant. No matter how much, 10, 12, 20, so more. However, you should keep in mind that within the framework of hypersonic small disturbance theory, m infinite or tau individually are not germane. The solution depends on this product. So, product of these m infinite tau, okay. As comes over the equation, we are dealing with, namely, expression, and notice that k is the parameter that appear, but not as a m infinitely and tau themselves. Tau also appears in the, if you remember, from the ratio beta over tau, which is one of the unknown of the problem to be obtained as part of the solution. Okay? And therefore, let us specify the value of k and set up a numerical solution for this value of k as follows. It will be several expressions. And first of all, assume a value of beta over tau. A suggested value might be for gamma 1.4, and note that this establishes as assumed value for the shock wave angle beta. Second, starting at theta average as beta over tau, yeah, a suggested value must be the same given by our previous equation, the last two equations here, and starting at the shock wave with the boundary values, we can numerically integrate in steps of minus delta theta, and that is in the direction of decreasing theta average, and that is starting at the shock wave, and integrate our equation in the direction toward the body. And this integration can be carried out by any standard numerical technique for a nonlinear ordinary differential equation, such as the Runge-Kutta-Missu, very famous from aerodynamics. And third, continue this integration until theta average reaches the value when equal 1, when our theta average equal 1, and then check to see if the body boundary condition is satisfied. And that is, if the relation from 1, function of 1, must be equal 0, and satisfied by the numerical integration. Satisfied or not? How do you think? If not, assume a new value of beta over tau, and repeat our steps 2 and 3. I'm recently, couple minutes, mentioned it. Repeat this process until the proper value of beta over tau is found such that our function from 1 equals 0. And final, fourth step, we have now arrived for the final result. For the specified value of k, we have found the ratio of wave angle to cone angle, or beta over tau, and we have obtained numerical values of f and f stretch between the shock wave. Why? Because the theta average is simply beta over tau, and the body in case when theta average equals 1. After the preceding numerical procedure, if complete, the conventional flow field variable can be obtained from F and F stretch. And we can obtain the pressure in case, as you can see at the bottom left part of this slide. Average pressure proportional omega in times rho in power minus gamma, or after transformation get us this one. In turn, the pressure coefficient can be combined as the form in the top of right side, divided by this expression by tau squared, and noting that k proportional of m in infinity times tau, the preceding equations become in more compact form, as you can see as the middle of this right side plot. Substituting our expression from this one and noting into preceding, we can obtain these form equation Cp over tau squared. It means the pressure coefficient on the cone surface can be obtained by inserting as the theta average equal 1. And the numerically obtained value from F value from the F stretch from 1 into this equation. The numerical solution to the preceding problem was first obtained by Van Dyck. Van Dyck's formulation differs from our preceding derivation in that he defined k as m infinity times beta, and utilizes beta instead of tau, as usual, in the non-dimensional variable. And this has an advantage in the numerical solution, because his conical coordinate is defined as r over beta times f, in contrast to our r over tau. Because beta over tau is an unknown, we were led to an iterative numerical solution. Iterative. That's very popular nearly 20, 30 years ago, because it has not many modern computers as we now have. So the value of his conical coordinate at f equals 0, it means the body boundary condition. The value as this yields the ratio of wave angle to cone angle. And in my opinion, for pedagogical reasons, we have deliberately chosen not to follow Van Dyck in this regard. Instead, we maintain a consistent usage of the body slenderness ratio tau instead of beta. Okay? And k must be proportional as a m infinity times tau throughout our development, because such usage was introduced right from the beginning of today's lecture, and having to do with hypersonic similarity, where k was initially defined as this, I remember, yes, m infinity time. Moreover, in practical applications involving a given body, we know tau, while beta is usually unknown. And hence, the practical hypersonic similarity parameter is m infinity times tau, but not infinitely times better, okay? Of course, in the final solution, the flow field results are the same, no matter which approach is taken. And this next figure, diagram on the right part, shows the final result for Cp over tau squared on the surface of the cone. And note from our numerical solution that a specific value Cp over tau squared on the cone correspond to the specified value of k. And when another value of k is chosen, so another value Cp over tau squared is obtained from the solution as a function of k, as known from our previous work, okay? And this function is given by numerical solution result, where we're plotting Cp over tau squared versus k. K equals m infinitely times tau. So the upper line is the present numerical solution. The two lower lines are exact conical flow results from Kopal for cone of 10 and 15 half angles. By the way, the solid circles in this diagram correspond to a closed form analytical expression to be discussed subsequently. And the value of this figure is that it illustrates the degree of accuracy of the hypersonic small disturbance theory when compared with exact result. Reasonable accuracy is indeed obtained over a wide range of value of k. The agreement is better for the more slender cone, as expected. Recall our earlier statement that the application of hypersonic small disturbance theory to the flow over a cone is given here partially as an academic exercise, an exercise to demonstrate for a relatively simple flow what the hypersonic small disturbance theory is all about. And now there is another reason for treating the case of a cone. For this case, the hypersonic small disturbance theory leads to a closed form analytical result for Cp, for our Cp expression, and better for given tau and m infinite. And this now becomes much more than just an academic exercise, because a closed form analytic result for our Cp for hypersonic flow over cones allows some very practical engineering calculation. For example, the tangent cone method discussed in our lecture number 3 becomes even simpler and more useful if we have a formula for our Cp on a cone, rather than constantly having to look up values in the Kopal table. Moreover, for certain optimization studies of hypersonic vehicles using the calculus of variation, a closed form expression for Cp is absolutely necessary. And therefore, we will end this module by discussing such closed form results, and thus illustrating one of the most useful advantages of hypersonic small disturbance theory. So, starting with equation of Rasmussen, integrating twice from the shock wave, obtaining an integral equation for function as theta, and by successive approximation, this led to closed form analytical expression both for f from theta average and f stretch from theta average as function of theta average. All these details are described in researches, in special researches, which, if somebody wants, may be encouraged to examine. And hence, no further elaboration will be given here. So, utilizing the fact that function from theta theta stretch equals 0 at the body surface, Rasmussen obtains the following closed-loop form expression for the shock wave angle. K sub beta proportionals K times square root from these two components, gamma plus 1 over 2 plus 1 over K squared. K sub beta here is proportionals M infinity times beta. And furthermore, by substitution, this closed form result for F stretch from theta, and Rasmussen obtains the following expression for the pressure coefficient on a cone, here, as you can see. In this analysis, Rasmussen approximated as tau can be tangent of the theta sub c by theta c itself. And hence, in this equation of the bracket, we have a K proportionals M infinity times theta sub c. And results from this equation are plotted as a solid circle on this our diagram. But we should note it from this equation agrees well with the numerical result of one die in case when K is a positive and higher than 1. Rasmussen observed in their research and agrees well with the exact cone result as made before him Kopal. In case when tau is small and M infinitely is large. However, better agreement for larger values of tau is obtained in case when tau is approximately equal theta sub c. And this allows us to replace the sign theta c. And this result will be shown in next figure, where the Cp over cosine, yes, theta is plotted inverted M inversely times sine. The open symbol are exact result from the Kopal. And the solid line here, as you can see here on the top, with theta c replaced by theta sine. An excellent agreement is obtained even for a reasonably large cone, semi-angle, nearly 30 degrees. And I should say that, Doty and Rasmussen extended his work to include angle of attack effect, defining for normal force coefficient C sub n proportionals normal force over 1 over 2 rho v squared times area or base area, a closed form expression for the slope of the moment coefficient curve. Yes, moment coefficient curve dCm over dA from alpha equator. Epsilon naught depending from M infinitely at sine angle. Okay? So now let's come to the next question of today's lecture. Let's analyze comments on hypersonic small disturbance field. So small disturbance or small perturbation theories abound in aerodynamics. in the areas of subsonic and supersonic aerodynamics. The small perturbation approach leads to linear theory, with correspondingly simple results. So why we using this method here too? But in contrast, hypersonic flow is inherently nonlinear. Even the small perturbation theory for hypersonic flow is nonlinear. Consequently, the hypersonic small disturbance theory is more elaborate and leads to more complex results. For proof, just compare the less lengthy discussion we have presented in this module with the analogous simple discussion for subsonic and supersonic flow that you can find in standard textbooks, such as this slide. Okay? However, despite its nonlinearity, hypersonic small disturbance theory does provide useful results for the analysis of hypersonic flow over slender bodies, witness the principle of hypersonic similarity. And in this case, the similar solutions obtained in today's lecture, as well as the closed form analytical expression presented at the end of this lecture. And for these reasons, hypersonic small disturbance theory occupies a relatively high status within the general class of approximate flow field solutions, certainly for hypersonic flow. And referring to our roadmap, as you can see on this slide, we now leave this subject. And for the remainder of this module, we move on to two other approximate hypersonic flow field methods, namely blast wave theory and thin shock layer theory. And also, regarding our module roadmap on this slide, we continue to travel down the center section, but at the next time. Okay? Next time we continue our course. And for this moment, I think it's enough for today. I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.